Test. Hi, good morning, everyone. Thanks for joining our webinar this morning. And so today we are going to talk about signal integrity for high-speed designs. And first, let's start off introducing ourselves. So we are Singularity Engineering. We are a simulation provider for the San Francisco Bay Area. We help many customers to speed up development, identify reliability issues, and optimize performance. We also support full Ansys portfolio of tools. So now we are going to go over the agenda for today. So first, we are going to diagnosing SI problems and what is signal integrity, and then we are going to talk about S parameter crosstalk, which includes far end crosstalk, near end crosstalk, and ground pound noise. We also are going to talk about the summary of the result, SI wave capability, and conclusions. So next, we are going to diagnosing SI problems. So first, we want to know what it looks like. So when you have SI problem, it's usually when your circuit doesn't work, or when you send an input but receiving inaccurate output, or when your circuit fails intermittently. When you do not have SI, like simulation tools, you will not know what happens during the design process. In this case, you have to do it the hard way, which you have to manufacture your design and test it physically. This will consume a significant of time and material investments. Sometimes, even during the testing process, you cannot find out where the problem is. So today we are going to teach you the easy way using simulation tool. SI Wave is a dedicated tool for electrical analysis of full PCB and complex electronic package. With SI Wave, you are able to test your design and check for the signal integrity issue before you manufacture it and make sure it works. This can save you time and money for effective production, especially in modern day when PCB designs are required to have faster speeds in a smaller device. In this case, there will be more SI problems increase. So next, what is signal integrity? Signal integrity usually addresses two issues, timing and signal quality. So timing means does the signal arrive at the destination when it's supposed to be? And signal quality means is the signal in good condition when it arrives. So at high frequency design, usually there will be a lot of negative effects such as ringing, crosstalk, reflections, and power ground noise. So all this effect can impact your signal and cause errors and system failure. So what are these problems? Crosstalk, ground, and power noise usually caused by signal interference. Ringing, reflection are usually caused by impedance mismatch. So here I have a few pictures shows you the eye diagram to show you when you have ideal power supply, when you have a voltage regulator module, or when you have a aggressor in like low frequency, like let's say 1.6 gigahertz, and there's a higher frequency at 4 gigahertz. So as you can see, it goes down the road, there are more noise and more noise. So I'm also going to, so this is our demonstration board today that I'm going to show you for today's testing. So let's first go ahead and launch SI Wave. So for SI Wave, you can import many different file types from many design tools, and Ansys can cover most of the design tool file types. So you can do ODB++, DXF, and many etc. So let's launch, let's say crosstalk here. So we have the design source here. And first, for SI wave here, you can verify your stack up. So here is for your different layer, you can modify the thickness, material, conductivity, etc. So you can modify all your layers here. And also there are many like path stack. These are refers to VR or any similar stuffs. And we all have circuit elements like inductors, capacitors, resistor, everything is included here. So you can access it in the home tab. Everything is very easy to see. So so first thing we are going to talk about is S parameter. As many engineers know, like in circuit design, we usually want to look at S11 insertion loss and S21, which is the return loss. So let's go ahead. And so first thing you need to do in SI wave to run a SYZ parameter is to create a port. You need to set up a port before you run the simulation. So here I set out a port for the MDQ12 and MDQ13 between two devices. So let's go back here. You can see a controller, a DRAM, and a voltage regulator module. So the controller acts like a driver and the DRAM is a receiver. So when it comes back, here you have the driver here. So we have the port set up between MDQ12, MDQ13 driver and receiver. And let's go ahead and compute SYZ parameter. Here you can set your start frequency, stop frequency. You can set the step size or number of points you want to simulate it. And you can just simply launch. And at the same time, if you want to see all your nets, you can access your nets. Everything is here. So you have single net, differential nets, and extended nets. And here's all your components and discrete device. So we have the result here. First, you can access your result here, or you can go to the result tab and your result shows here. So let's go here. We can just simply double click it. So here you can show self terms, which is S11, and you can also see your transmission terms, which is S21. At the same time, you can also plot your S11 into the electronic desktop for comparison purpose. Let's do it. Okay, so we have so many here. Okay, let's plot another one. I'll probably just do one at this time. If go ahead, plot. Yes. I'll delete all of this here. And right now you can see if you click on this one, you only have one plot. You click on this one, you have another plot. But if you pull it over, you can just drag and drop. Then you have two plot and you can see the comparison. In this case, maybe I have the same one. So let me plot another one. So you can see your difference more clearly. So drag and drop. See, now you can see the difference. Okay, so So the next thing we want to talk about is crosstalk. So we usually do time domain crosstalk here, but we can also do a frequency domain crosstalk. So if we go to crosstalk, you can just do a time domain crosstalk. We also want to do it between the MDQ12, MDQ13. So we just want MDQ12, MDQ13 next. And here you have your reference design, which is the driver, receiver, and you can set up your driver rise time, and you can set up your driver voltage and the input impedance. So we just set everything as default, launch, and the simulation is done. So you can see the peak voltage here. So this is indicates like here, this cylinders here indicates like the crosstalk between MDQ12 and MDQ13. Here's the same. Or if, let's say, if you want to see more nets, we can go ahead and input more. Yes. So as you can see, under the simulation tab, you have many type of simulation you can do, like DCIR, which is the power integrity. You can do resonant modes, and you can do frequency sweeps, far field, near field, and many other stuff. So let's look at the crosstalk. Right now, you can see all this crosstalk between, like, from MDQ9 to MDQ15 nets. So here, let's click on one. Right now, the one I'm clicking is MDQ12 and MDQ13. Okay. So here you can choose either you want to see far end or near end crosstalk. So if you see near end, this is your near end. If you click on far end, this will be your far end. And if you scroll down, so if you want to see a plot, you need to click on one cylinder, then you show your plot. So right now we have the far end and near end displays here. Or if you want to see V in, V out, so this is the V in and V out. So let's see it more clear on the pictures here. Right now we have the crosstalk, and we can see here's a V in and the V out. So usually when you see the near end crosstalk, this one is the near end crosstalk. Near end crosstalk is related to the input voltage. So the time of the rising time for the V in is the time that the crosstalk happens. So as you can see, the width of the time rise is the same as the crosstalk that happens. Okay, next we are going to talk about the eye diagram. So here is a simply picture shows you what are all those factors in the eye diagram. So in the eye diagram, we have jitters, timing jitters. That's the timing errors that results from misalignment of rise time and false time. And definitely the smaller slope is better. That means less timing error. And we also have the signal to noise ratio at sampling points. So that's the ratio between signal power and noise power, but higher ratio is always the better. And we also have the distortion. This is related to the SNR, so the signal to noise ratio. And also, if the amount of signal that's beyond the distortion, that's the wasted power for the eye diagram. So next, we are going to talk about far end crosstalk and near end crosstalk for the eye diagram. So far end crosstalk is coupling between two or more transmitting pairs as the signal propagates in the same direction from the driver to the receivers. And in this case, as you can see, in this eye diagram here, this is just the victim line itself. So there's only one trace between driver and receiver. And in this picture, you can see there are two traces. So one victim line and one aggressor line. So as you can see, the noise here appears more than the picture one. So which means there's crosstalk between them. And so if you can see, when the signal sending from the driver to the receiver, the rising edge will cause a voltage interference. So you can see there's a bulging there because when the signal is sending at the rise time, the aggression lines keep aggressing on the victim line at the same point. So you can see the bulging here. And so always faster rise time creates more crosstalk, and far end crosstalk can increase jitter and eye closure. And in this picture, it shows you like the rise time of the input voltage. The input voltage is when the crosstalk happens. And in this picture, you can see it more clear. So there's when you have a signal, just a victim line itself, and there's an aggression line, and you can see there's a bulging here. So the next is a near end crosstalk. So near end crosstalk measures the signal coupling between two nets. So instead of far end crosstalk, the signal propagating in the same direction, near end crosstalk is measure the crosstalk of two signal propagate in opposite directions. So in this picture, you can very easy to see. So this is aggression line. Let's say the signal propagating this way, and if for the victim line, if the signal propagating this way, we call it far end crosstalk. If we go back, the signal will go back in the second way, the other ways. Then it's a near end crosstalk. And near end crosstalk also gives you jitters and eye closure. And at the same thing, faster rise time creates more crosstalks. And so let me show you the demo for the crosstalk. Let's go ahead, pull SI wave. So in this picture here, we have, so let's go ahead, do a simulation. So for the eye diagram, you need to use a SI wizard. This is used if you want to simulate the, if you want to get your eye diagram. So right now, let me show you just the victim line itself. So right now, if we just do MDQ13, so if we go next, so here you can see you have a receiver driver. You can input your IBIS model. And then you can set up your excitation source. You can manage your source here, and you have your input, and you have your bit rate, which is a frequency. You have your delay, rise time, false time, internal impedance, etc. If you go next, so here you can set up your power supply. So let's see here. So buffer node internal voltage means ideal power supply, so it doesn't give you noise. And voltage regulator module gives you noise. So in this case, we're going to use voltage regulator module for now. And this is a power net. Let's go next. This is the voltage regulator module circuit diagram. So you can define your circuit elements here. And next, you set your step size, stop time. We can just go ahead, OK. And it will launch in the electronic desktop automatically. And if you want to do an eye diagram, you don't usually need to set up ports. When you select the net, it will set up port itself automatically. So in here, you can see the, so here's the circuit model for this side is the driver, this side is the receiver, and here these symbols to create the eye diagram, and these symbols connect together to to define the circuit between these two devices. And you also have this one is the voltage regular module circuit. And right now the simulation is done. If we go to result, create a diagram again. So you can see there's a, for MDQ13, you can see TX and RX. TX means the transmitting end, which is the driver, and the RS is the receiving end, which is the receiver. So we are going to see both of them. So TX, RX. Okay. So when we see the receiving end, that means the far end crosstalk. When you see the transmitting end, that's the near end crosstalks. So these are the crosstalk you can see. So what happened if, oh, this is just victim line itself. There's no aggression line or anything. Don't. And if we go next, let me show you if we have the, when we have the aggression line. So you can just go ahead and add an aggression line. So MDQ12 is right next to MDQ13. Just go ahead. Okay, everything set up correctly. Next, okay. Yes, we just want to reload it. Okay, while this is running, one thing I forgot to show you is when you have the crosstalk here. So in this picture, you can see the crosstalk right now is around, for the MDQ12, MDQ13 is around like 0.012 volt. And that's because there are two traces so close to each other. Let's see what happens if we move it a little bit further apart. So let's move it right here. And just go ahead, delete this point. Just move it a little bit further apart. Okay. We can just, and then let's do another simulation for time domain crosstalks. So in SI wave, you can also move your traces around very easily. So when let's say when you have input design and then you just want to make a minor change, you can always modify it in SI wave. Just simply drag and drop, or you can use tools, add like LOM elements and everything, or generate. You can do anything you want here. So here we can, let's look at the crosstalk again. So we were looking at MDQ12 and MDQ13. So MDQ12, MDQ13. At this moment, we can see the peak voltage is dropped to 0.005, which is only half of the peak voltage before. So the distance between traces matters for the crosstalks. So let's check if the other one is done. Yes. So let's go ahead. So we were looking at MDQ13. So TX is transmitting, and so let's look at the far end crosstalk first. So as you can see, there appears more noise than without victim lines. So here's a Baojun. And if we look at the near end crosstalks, you can see it appears more noise as well. So if we go back to here, so if we look at the near end crosstalk, so far end crosstalk here has less noise, more noise, Baojun, and for near end crosstalks. So for near end crosstalk, since the signal is propagating in different direction, the aggression line is aggressing on the victim line at different points. So the noise will appear more spread out across the eye. So here you can see the noise is everywhere across in the eye compared to this one. And here you can just see a bit more noise at this point than the far end crosstalks. And next, so I'm going to show you the power and ground bounce. So for power and ground bounce, power supply can act like a victim or aggressor. So when it is a victim, is where the serial data line. So that's when the serial data lines are the aggressors. So the best examples to define this is simultaneous switching noise. So that's when current flows from the device to the system, from the device ground to the system ground through wire, or let's say it's package traces and solder board to the board ground. So you can see here, in case of fast switching of I/O pins, these interconnecting elements can act like an inductor. So due to variation in current across inductors, voltage drop occurs. So now that's when the device ground has different potential than the system ground. So you have a different voltage between these two ground. So in ideal case, when the device ground and the system grounds are equal, the output signal should have the same voltage value. But when their grounds are not equal, so that's when the ground bounce happens. The output voltage is different. And so what happened? So that's a case of power supply as a victim. So what happened when the power supply is aggressor? So that's usually, so as we know, power supply can have a lot of noise, and those noise come from many different environments. So let's say so like an amplifier. So like any power supplies generate low level of noise. So for example, thermal noise. While switching mode power supplies generate noise from switching transistors. When linear regulate, so in this case, when you are when you are switching transistor, that will generate thermal noise. So that can be one of the power supply noise, and that's going to affect your signal transmitting between nets. And at the same time, higher input frequency can also result in more crosstalks. So, and power and ground bounce also increase jitter and eye closure. So in this picture here, you can see the top one is with ideal power supply, and the bottom one is with the voltage regulator module. So it's not an ideal power supply. So let me show you in the simulation. So if we go ahead and do another simulation, we just do the same thing. Next, as I was mentioned, you can choose your power supply here. So buffer internal voltage is the ideal power supply. So if we click next, So remember this picture. This picture is with the voltage regulator module. So what happens if we have just the ideal power supplies? So while it's running, let me show you this. So when you have the eye diagram, you can input a mask. The mask is used to indicate how open your eyes want to be. So in different designer wants the eyes to open. They have different goal of like how the eye is open. So the mask you can in electronic desktop you can input a mask. So the mask can measure if your eye is open wide enough or is not enough. So in that case, you can text to see if that's the result you want to be. So when the eye opens enough, that means you have the signal transmitted properly in your as you expected. If not, then you need to make some changes. So I believe. So in this segment, in the picture here, you can see there's no voltage regulator circuit anymore because you are using an ideal voltage source. It might take a while. Okay, so let's just go ahead and go. I believe there's a. Yeah, so as you can, so it might take a while. It might. Yeah, so just give you an idea. In this picture, you can see this one is without with ideal voltage source. I mean ideal power supply, and this is without ideal power. It's with a real power supply, so you can see the difference very clear between these two. Okay, so let's do the summary of the results. So when you oh yes, so another thing I want to show you is okay. That doesn't matter. Okay. So usually in testing, we want to test all the nets between two devices. So let me just go ahead abort this. Okay. Anyways, let's all open another demo. So let's do the eye. I'm just going to terminate this. Okay. Okay. So usually we want to just measure the all the nets that transfer signal between two devices. So in this case, if we want to see what are the nets between these two devices, the driver and the receivers. So here is MDQ8 to MDQ15. So here you can see all these nets connected between these two devices. And if we just go ahead and run a simulation between all these nets, add next, and we'll leave everything as default since I already input the IBIS model and power supply next. Okay. So for this type of simulation, it usually doesn't take that long. That's another great thing of SI wave. Like let's say I have I have 7 nets right now between these two devices. It usually take less than a minute or around a minute. So that can save you a lot of time to do like if you just run a simulation, it can save you a lot of time to find out what the problem is. So you can see if depends on how many nets you have, it generates all these driver circuits and receiver circuits. That's weird. Okay. So let me. Okay, so to save your time, I can just show you the result directly. So here, when you have your trace is just connected like this, then it gives you closed eyes because your trace is not placed properly. And when you arrange your trace into the proper space, it gives you open eye, and you can add a mask to make sure see your eye is open enough. That meets your what you expected, meets your expectation. And so you have the closed eye, you have the open eye. That's what happened by just doing a simple changes. And so to conclude our topic today, we have S11 as parameters. We have insertion loss, return loss. You can plot it in the electronic desktop to see the differences. And we have the time domain crosstalk. So if you move the traces, put the traces close to each other, you have a more crosstalk happens. And if you just move them a little bit far apart, you reduce it by half or more. And also we have all these eye diagrams. So as I mentioned at the beginning, you have the ideal power supplies. You have the using the voltage regulation module with no aggressors, and you have the voltage non-ideal supply with aggressors. And this is at 1.6. This is at 1.6 gigahertz, and this is at 4 gigahertz. So you can see the noise increasing, like very straightforward between these eye diagrams. So there are some other SI wave capability. We have the EMI scanner that can quickly scan entire design for rules of violation, which can cause EMI problems. We also can do some power integrity stuff. So we can compute DCIR. We can do capacitor optimization. We also can compute resonant modes that can highlight the potential potential problem areas of the PCB package. Also helps to indicate the impedance at particular frequency. We can do impedance scan that can scan the net impedance between devices or on your PCB design. We can do a TDR wizard, that's the time domain reflection. We can also compute RLGC, that you can extract your value of RLGC of the design at certain frequency. And we have many other capability. So to conclude our topic today, as the demand for high frequency circuit increase, signal integrity problem will also increase. So in order to save your time and to save your money on material investment, simulation tool is definitely the great tool to help you to create effective productions. And Ansys SI Wave can provide you a powerful and easy to use solution for electronic designers. If you have further questions, feel free to contact us. So my name is Zefan. I'm the application engineer at Singularity Engineering. And below is my email and phone number and our website. So feel free to contact me if you have any question. And I will post this video on YouTube later, so you can also comment under YouTube. And thanks for joining the webinar today. Thank you.